same, or do we have to do more than that? What else do we have to make sure of? We've made sure that we don't change the magnetic field, but we also have an electric field here, right? If we change A, then of course there's going to be an extra term here that is not necessarily zero. Right? We've constructed it so that the curl of A doesn't change, but the ADT can change. Right? So that means, what can we do? We probably have to do something with the scalar potential as well. So the scalar potential V, let's write this, plus, so it must be V prime plus some V plus, actually it would be consistent with the notation in the book, actually, that we write this as. Just a little, sorry about that. So, add some kind of function beta to this, and that beta somehow must cancel out the term that comes in here from the A over dt. Right? So, what we then have, so the electric field better be the same. So, we write the electric field, well this was minus d, gradient B, minus dA over dt. That better be the same as using A prime and B prime, right? So that's minus gradient B minus gradient beta minus dA dt, but this is dA prime, dA dt minus d alpha over dt. Right? And now, if these two are the same, that means these two correction terms have to cancel out. Right? Of course, so that means that we better guarantee that gradient beta plus d alpha over dt equals 0. But alpha, we've already said, must be the gradient of something. Right? So that means we can write gradient beta plus gradient of d lambda over dt equals 0. Or that means, well, gradient of beta plus d lambda over dt equals 0. So that means that whatever is in here does not depend on the point in space. It can depend on time, but this must be the same everywhere, because the gradient is always 0. The gradient of something is always 0. It has the same value everywhere. So this means that it's independent of, well, wherever you are in three-dimensional space. So that means this is effectively some kind of constant in time, in space. So that means modulo some normalization constant. We can simply set our beta equals minus d lambda over dt. So that means what we find, what we call gauge transformations, so transformations to these potentials A and B that don't change the fields is changing A to some difference A, that is the old one, plus, so now this alpha was gradient lambda, right? And B would then change to B prime as B minus B lambda over. So that is the freedom we have. If you start out, for example, if you know your charge and current densities, maybe you get lucky and you can actually solve this for B and A. You start out finding some potentials, A and B. Then you can choose any arbitrary function lambda, add the gradient to your scalar vector potential, subtract the time derivative from the scalar potential, and the physics doesn't change. The fields don't change, and of course, you're given the charge and current densities. So, any questions on that? Does this make sense at all? Okay, good. The camera, just think about the fact that if you actually Google my name, you'll actually find that I'm a German television actor, so the camera is totally appropriate. But for a while, actually, Googling my name, you saw my picture there with the legend German television actor. They fixed that by now. Okay, good. So now, let's see if we can use this somehow to simplify these expressions that we have here. Right? So the relation between the charges and current densities and the potentials, see this can get kind of messy. Right? Let me actually write this up here that I can. So let's write this down here again. So we have gradient plus over T equals minus rho naught. And we had divergence gradient of T. So let's see if we can use the fact that you have that freedom there to simplify these equations. You can imagine that in many cases, a differential equation like this with tons of double derivatives here and A and B mixed into each other, that's typically way too messy to actually solve that directly. So let's see if we can find a somewhat more convenient way to simplify these potentials. Okay. And there's in fact two different, so we call them gauges now. So changing your potentials of these functions, that's what we call gauge transformation. So any specific choice that we now make here, that's called a gauge. So a specific way of writing the potential. So there's two gauges that are quite often used here. lead to something that you're quite familiar with. It's called the Coulomb gauge. And for that, we do a transformation so that this divergence term here, divergence A, becomes 0. So if we transform our potentials so that the divergence of A becomes 0, then what simplifies? And this term, of course, drops away, and this term, fortunately, everything else here stays. But let's see why this is called Coulomb gauge, because we have the Laplace of E equals minus rho over epsilon naught. And that should look familiar. This is what you know from the static case. From the static case, you could write E as the gradient of V simply. That means the gradient of E is the Laplace of the potential. So this looks quite familiar. And then, well, this we actually know how to solve. Right? How do we solve that? So if you have now your charge distribution here, this is your rho of r prime, and you're somewhere at some point r. You see the potential. We call this connection vector r, that's this r prime. So this is this old German script type style r here. And you can write the potential at r in what form? That I'm sure you have seen, right? Concept of Green's function coming in. Something, right, where you integrate over your rho of r prime, right? And what other factors come in there? We know that the plus of something is this function. You can get the potential by integrating. What other factors come in there? This you must have seen from the electrostatics. What do we divide by here? Well, somebody must remember. Divide by the length of this distance vector, right? So r is just the length of r. Right? And it's a normalization factor, obviously the epsilon naught has to come in here, and this is actually normalized to 4 pi, right? 4 pi epsilon naught. Does that ring a bell? Look familiar? So I'm pretty sure you must have used this. So then from there can be, from the static case, you also know that you can calculate the electric field as minus gradient V, right? Or it would be actually the minus 1 over r. So that's 1 over 4 pi epsilon naught rho of r prime d3 r prime over r squared. Is that true now? This probably you also remember, right? This you've certainly also seen in electrostatics. essentially just take the gradient of this. And at some point, probably next week, we'll actually go through again how to calculate this derivative. Is that still true in this page? Is that the correct expression for the electric field or not? Hands up who thinks it is. No abstentions. Hands up who thinks it's wrong. No abstentions. So let's try that again. Who thinks it's right? Who thinks it's wrong? Let's try that again. No abstentions. You must have some opinion. Is this correct or is it not? Who thinks it's correct? Who thinks it's not? Okay, we're converging to some consensus here. Very good. So why is it wrong? It's correct that it's wrong. Why is it wrong?
It's not static.
Say again?
It's not static.
It's not static, right? So what else comes in here? We've only set the divergence of A to 0, right? But we still have the dAdt term. Right? So we still have to add the dAdt to this, right? Minus dAdt, whatever the A is, right? That is generally not zero. So now it's correct. Very good. Okay, so with that, so our essentially Poisson equation here for the scalar potential, that becomes simple, but a little unfortunate is that this term, so the calculation of A from the charge density still becomes quite messy. So we still have up there, so only this term drops out. We still have mu naught, epsilon naught, gradient of dt minus G, and in the general case, this can become quite messy and usually not normally tractable. So that's what we call this Coulomb gauge, because essentially we recover Coulomb's law here, but it's convenient really only if we are in a static situation that all these time derivatives drop out. Then it's nice. If they don't drop out, then this actually becomes quite nasty. Not really usable for any practical purposes. So let's do one other choice here. The other choice that actually makes the thing really nicely tractable and symmetric, that's called the Lorentz gauge. For that, we actually just cut out this entire term. So the divergence A, we set it not to 0, but we set it to just cancel out this dAdt term. So for the Lorentz gauge, we set the divergence A as just minus mu naught epsilon naught into V over T squared. That is right. term here drops out, right? So if we use that, then we have the Laplace minus mu naught epsilon naught d2 t squared a equals mu naught j. And yeah, now we've done something nice here and dropped this entire term out. But now, of course, divergence A here isn't 0 anymore. Because divergence A minus mu naught epsilon naught dt. So, with that in there, we get the divergence, the Laplace of V minus, see, divergence A is this. We have another minus ddt of that. So it gives us minus mu naught epsilon naught d2 over dt squared V equals, sorry, minus epsilon naught. Right? So now, at least, they're both equally complicated, right? And so everybody remembers, of course, what mu naught epsilon naught is. Second? 1 over c squared. Very good. Right? 1 over c squared. So the term that we have here, so this differential operator minus mu naught epsilon naught d2 over t squared. That operator, of course, has all the spatial derivatives in here, right? d2 dx squared plus second y derivative plus the second d derivative, z derivative, and then we have minus 1 over c squared, 2 over t squared. Right? So, and towards the second half of the class, you'll see that this is actually a very nice, just special relativistic generalization of these derivatives in 3, now in 4 dimensions. Because this, of course, second spatial derivative here. And, well, CT is another spatial component, right? So this is just 4 spatial derivatives in a row. Only that we have added this time derivative here with a different sign. And this will all make perfect sense to you when we start discussing special relativity in detail, starting in 5-6 weeks or so. So for now, let's just accept this as it is. And it's called something called the D'Alembert operator. You just write this as a squared square. So it's called a D'Alembert operator. So with that definition, of course we have our connections between charges and currents and the potentials as simply the D'Alembert A equals minus mu naught J, and we have the D'Alembert B equals minus rho over epsilon naught. Of course, from here to here, we've really not done anything other than just rewriting this differential operator. Good. I usually try to time a little break so that we can join the coffee tea break downstairs, which is in just a few minutes. So, any questions, any comments on this? Any concerns? So the next step that, we won't get to it, that's actually stuff of next week, but we will start with the mathematical concept of Green's function that we can then derive to actually solve this equation. Does anybody remember or recall what a Green's function is? Have you heard of this concept of a Green's function before? Can you explain what it is? Okay. Maybe we should take a bit of a break now. Coffee, tea should be ready in a few minutes. And then maybe when we 20 past or so.